Hey, welcome back, everybody. This is Pre-Calculus Day 7. We're going to talk about transformations of functions. So the whole goal of today is to take the graph of a function and stretch it, compress it, move it horizontally, vertically, reflect it through x-axis and y-axis. That's going to give us a lot of flexibility, not only to translate graphs, but really to understand what graphs would look like given an equation, which is a really valuable skill to have in mathematics. So let's start off by recalling the following. So this was one of the functions from our library of functions. So yeah, let's recall some facts about f of x equals x squared. So we know that this is our sort of classic parabola with its vertex at the origin. It opens upward, or we would say it's concave upward. And let's just recall that the domain, remember that was the set of legal inputs, the domain of the function is the open interval minus infinity to infinity. That means I can plug in any x value that lives inside of this interval, and I can expect a meaningful output after I plug that x value in here. Now the range, that's the set of outputs. This function will only output values from 0 to infinity. And what about symmetry? This, of course, has y-axis symmetry. And we said that that would make it an even function. Remember that even functions have y-axis symmetry. And I'll just remind you again, that's an even function, y-axis symmetry. Okay, so what we want to do is let's start a little bit of an investigation that's based on a variation of this. And so let's see what effect adding 1 has to the graph of f of x. So we'll call this, investigation. And so, basically we want a graph, let's say g of x equals x squared plus 1. And so we'll start off by making a table of values. In general, we don't want to do this, but that's actually helpful right now for developing intuition. And let's pick some values. How about -1, 0, 1, 2, and 3? So maybe we're expecting some variation of this. Okay, let's see. So I'm going to plug x in for x. So I'm dropping -1 into my function machine, right? And compute, and that's going to output a y value. So that gives me, it looks like 2. Next, I input 0 into my function machine. That's going to output a 1. And we're going to keep going in this way. Okay, so let's sketch the graph, give a basic sketch based on these values. So I don't need any, looks like I don't need any negative values of y. Okay, so I'm putting a scale on x, and then maybe my y scale, maybe it'll be a little tighter so I can fit it. I could also go by 2s if I wanted to, etc. I'm just going to go by 1s, that seems fine. So etc. And let's see here. So we've got -1, 2. So -1, 2. Looks like 0, 1. There's 0, 1. And then we've got 1, 2. So just plotting points based on our table. And then we've got 2, 5. So 2, 5. and then it looks like 310, and that'll be enough for a sketch. That'll be enough for a sketch. So that should be just fine. Let's say there's 310. So I'm going to connect. I get this concave upward parabola. And the idea is that this is essentially the graph of this, but shifted up 1 unit on the y-axis. So let's note some things here. What would be the domain of this, aka what would be the set of legal inputs? Well, the domain actually hasn't changed. So the domain would be the open interval from minus infinity to infinity. But what about the range? The range has changed because, well, all the values got shifted up by 1 unit. So notice that the range is now from 1 to infinity. Again, the range is the set of outputs. And this still has y-axis symmetry. Okay, so it appears that if I add 1 to my original function, it takes the graph of the original function and shifts it vertically upward by 1 unit. Okay, so what happens? Let's see if... So we expect maybe if we were to subtract, maybe the opposite would happen, but let's see. Let's investigate. Okay, so yeah, new investigation. So yeah, well, let's sketch g of x equals x squared minus 1 this time. So a little variation. And again, we're going to start with a table of values. So here's x, here's g of x equals x squared minus 1, and my output's y. We're going to pick some values. Again, let's go just minus 1, 0, 1, 2, and 3. And we'll go ahead, fill out the table, and then give a sketch of our function g of x. All right, so we're plugging in minus 1 into our function machine. So that computes, and it looks like it's going to give me 0. So I plug 0 into my function. So that gives me minus 1 as an output. Going to now plug 1 into my function. Looks like I get 0. I'm going to plug 2 into my function. So that gives me 3. And then lastly, I'm going to plug 3 into my function. Compute it. That's going to give me 8. All right, so yeah, let's now give a sketch. Now, since my scales aren't the same from this graph to the previous in terms of spacing, if I were to measure, there's going to be, of course, some distortion. If you graph anything by hand, there's going to be some distortion. So just be mindful of that. And it looks like y, I need to go, so minus 1 down here. And I want to go to at least 8. I like to, if possible, go at least 1 over. Just a preference. I'm going to go a couple over. And we'll just plot the points, right? Minus 1 comma 0 is right here. And then 0 comma minus 1 is right here. And then 1 comma 0 is right here. And we're just continuing this way. So 2 comma 3. So 2 comma 3 is right here. And then 3 comma 8. And that should be sufficient for a sketch, right? We're just giving a sketch of the graph. And so it looks like our suspicion was true, that if I take the graph of the original function f of x equals x squared, and I subtract 1, it's going to be a vertical shift downward of the original by 1 unit. Okay, so let's do a little bit of practice. Let's give really sort of rough sketches for this, just to make sure we really understand the concept. So I'm going to say a sketch. Let's say A is g of x equals x squared minus 4. and b is, let's say, g of x equals x squared plus 3. Okay, so based on our observation, this should take the graph of x squared and push it down 4 units. So that's not too bad. So again, we're just given a basic sketch here. So here's minus 4, and our graph should look like this for A. Okay, so there's our rough sketch of A. Do you see how powerful that is? So you're starting to see the value in this. I can look at an equation and mentally visualize the graph without having to draw it. And that gives me a lot of information very quickly. All right, so based on our observations before, we should take the graph of y equals x squared and just slide it up 3 units. All right, so good enough for a sketch. And now let's look at some horizontal shifts now. So these were vertical shifts, right? Shifts upward and downwards. Let's look at some horizontal shifts. Okay, so yeah, through these investigations, we develop our intuition. And let's look at g of x equals x minus 2 quantity squared. And we want to understand what happens to the graph. What kind of shift of x squared is this? So again, we're just going to look at a table of values. Okay, so we're going to pick some inputs. How about 0, 1, 2, 3, and 4? We'll plug each into our function machine, and that's going to output a y value. So let's see here. We're going to plug in 0. Oops, that should be 0 there, not 2. And so that's going to be minus 2 squared, which is 4. So now I plug in 1. So that'll be minus 1 squared, which is 1. So now we'll plug in 2. So it'll be 0 squared. 0 squared is, of course, 0. And then we're going to plug in 3. So 3 minus 2 squared. That's going to be 1 squared, which is 1. And then we'll plug in 4. Well, 4 minus 2 is 2, but 2 squared is 4. So we at least have some points. And let's see what's happening with our graph. So it appears I don't need any negative y values here. And for x, let's say here's minus 1. Let's say here's 1, here's 2, here's 3, here's 4. How about one more for good measure? And then on y, let's say here's 1, 2, 3, 4, maybe one more. Maybe another one. Okay, so let's plot some points. So we've got 0, 4. So 0, 4 is right here. And then 1, 1, well, 1, 1 is right there. 2, 0 is right here. 3, 1, and then 4, 4. Now, of course, I could plot more points just by picking more x values and computing my table, but this is, again, sufficient for a sketch. Okay, so this is interesting. So we, in a sense, subtracted from x, but it shifted the graph to the right. It actually makes sense when you really think about it carefully, why the graph shifted to the right. Notice that in our regular or our parent function, so let's note this. So in our parent function, that's y equals x squared, or f of x equals x squared, we could ask ourselves the following question. So which choice of x creates a y value of 0? So I'm doing this sort of vertex centric. So which choice of x creates a y value of 0? Well, if x is 0, I get a y value of 0. So think of the same question over here. Which choice of x creates a y value of 0? Notice that it's a larger choice of x that creates a y value of 0. So the vertex shifted to the right, and therefore all the rest of the points followed and also were shifted to the right. So yeah, a larger value of x, aka further to the right, was needed to create a y value of 0. So this shift to the right of 2 units actually makes sense. So let me write this observation. So I want to say that g of x equals x minus 2 quantity squared is the graph of f of x equals x squared translated to the right 2 units. Okay, well, similarly, let's investigate what happens if we add something to x. Also, I want to encourage you not to think of, this is like a backwards effect. Think about this logically. Again, this makes complete sense because it took a larger choice of x to create a y value of 0. Okay, so yet another investigation. And so now let's say we've got g of x is equal to x plus 1 quantity squared. Again, we want a graph and basically see what happens to the graph of x squared. Okay, so we're going to make a table of values once more. And let's see here. Let's pick, how about -2, -1, 0, 1, and 2. All right, so let's go ahead and plug in -2. So -2 plus 1. So -2 plus 1 is -1, but squared is 1. So now let's plug in -1. So that's going to be 0 squared, which of course is 0. Now we'll plug in 0. So 0 plus 1 is 1, squared is 1. So now we'll plug in 1. So that's going to be 2 squared, which is 4. And then we'll plug in 2. So that's going to give me 3 squared. And 3 squared, of course, is 9. Okay, so let's see what happens here. All right, just putting a scale on the y-axis now. Again, my scale, of course, is not perfect, so there will be some distortion. Plus, my beautiful art skills help with that. So let's see what happens here. So, okay, so we've got -2, 1. So -2, 1. We've got -1, 0. We've got 0, 1. We've got 1, 4. So 1, 4. We've got 2, 9. So 2, 9. That should be a bit smoother. That shouldn't be sharp. That should be smooth. There you go. Okay, so something like that. Again, that's good enough for a sketch. So interesting, right? So we added to x and the graph shifted to the left. Let's see why that happened. Well, we can apply the same reasoning as before. So again, remember when we were looking at our parent function from our library of functions, so y equals x squared, or f of x equals x squared. we had the following. So I asked you here, so which choice of x creates a y value of 0? That corresponded to the vertex there. Well, we can play the same game here, right? So which choice of x creates a y value of 0? Well, if x is -1, I get a y value of 0. So notice it took a smaller x, an x that was further to the left, to create a y value of 0. So that's why the vertex was shifted 1 unit to the left in this case, and notice all the points follow. And so, of course, we can make the same sort of observation. So in this case, we could say that, well, g of x equals x plus 1 quantity squared is the graph of f of x equals x squared shifted or translated 1 unit to the left. Now, hopefully, now that we've developed some intuition, we can give some formal rules. So this is pretty cool because now we can take a graph and shift it up and down all we want, left and right all we want. So vertical and horizontal shifts. Well, the first thing I want to say is when I talk about c, the constant c, it's a positive real number. So I'm going to say let c be a real number such that c is positive. So one, let's talk about a vertical shift c units upward. Well, that's exactly g of x equals f of x plus c. That's going to take the original graph of f of x and push it upward c units. So just like x squared plus 1, or x squared plus 100, takes the graph of x squared and shifts it upwards this many units. Now, of course, we could talk about a shift downward. And, well, that's exactly f of x minus c. And then we mentioned before the horizontal shifts. Now, they seem backwards, but with a little care and thought, they make complete sense. So if I want to take the graph of f of x and shift it c units to the right, I want the following. So g of x is equal to f of x minus c. So that takes the graph of f of x and shifts it c units to the right. And then, of course, I could do a horizontal shift c units to the left. And that would be g of x equals f of x plus c. So what's nice now is that we can put these together. Say I wanted to do a shift to the right by 2 units and a shift upward by 3. I can do that. So for me, here comes the power in this thinking. So I could take something like this. So let's say we wanted to sketch. Let's say g of x equals x minus 2 quantity squared plus 3. Well, since I'm very familiar with the transformation rules, I can just look at this and know exactly what the graph looks like. That's incredibly powerful. Sort of the algebra here invokes a geometric picture. So let's dissect this. What do we want? Well, this will shift our graph to the right 2 units. So specifically here. And this will shift our graph. And when I say our graph, I mean the graph of the parent function f of x equals x squared. So this will shift that parent function up 3 units. Now, when drawing this, it might be helpful to follow the vertex and follow the y-intercept. So maybe I'll get those pieces of information. So the vertex, so instead of being at 0, 0, that will be shifted to the right 2 units and up 3. So the vertex will be at 2, 3, because that's where 0, 0 lands if I do this. Now, how do I get the y-intercept? Well, of course, we just let x equal 0. Because if x equals 0, you're on the y-axis. Okay. So yeah, let's let x equal 0. So what is that going to give me? That looks like negative 2 squared. So that's 4 plus 3. So the y value must be 7. So we said that the x is 0 and the y is 7. And honestly, if I'm giving a really light sketch, these might be enough. Again, just for a very, very quick sketch. That all depends on what your application requires, what your professor requires. But if I just want to give a little sketch, I think this is okay. So here's our vertex, and we're going to cross through this point as well. Okay, so again, it's just a sketch. Just a sketch. Oh, those art skills. How lucky are you? But that should be a parabola. That should be a nice parabola. But you get the idea. You can see it's the sort of home base parabola, the parent function parabola, shifted over 2 and up 3. That's exactly what's happening. All right, let's try yet another sketch. So let's say we want to sketch y equals x plus 1 quantity squared. Let's say plus 2. Okay, and again, let's keep in mind our parent function, which is y equals x squared. And so this will take this graph and shift it 1 unit to the left and 2 units up. And so yeah, if we're going to give a really, really light sketch, just to invoke that idea, we could say, well, maybe there's the vertex. And there's our graph. Okay, so yeah, this was this graph, pushed to the left 1 unit and pushed up 2 units rather. Well, it turns out we can do this, of course, on more than just parabolas, right? We've got a whole library of functions. So now we can apply this in a wider context. So for example, say I wanted to sketch, let's say g of x equals x plus 2 quantity cubed. Well, the parent function in this case will be the cubic. Right, so the parent function is f of x equals x cubed, which looks like this. So this point right here, we don't call that the vertex, we call that the inflection point. You'll learn more about that in calculus. But this, it's not quite a vertex because it's not a max or min, but this is an inflection point. Okay, so for us, what do we want to do? We want to take this graph and we want to shift it, it looks like to the left 2 units. So we're going to take this and just slide it over. That's essentially what's happening. Okay, so again, just giving a light sketch. So we have something like this. Right? So it's just this graph just slid over 2 units. So you can see that's nice. Once you learn the basic principles, you can apply it to a variety of functions. So let's say we want to sketch. Let's look at y equals the absolute value of x minus 3 minus 2. And of course, we want to recall the parent function. That's y equals the absolute value of x. And remember, it looks like this. It's got a really, really sharp corner here. But we also want to remember how that's truly defined. It's defined as a piecewise function. So the absolute value of x is equal to x for x non-negative, and exactly minus x for x negative. So what does this transformation do to this graph? Well, we're going to push the graph over to the right 3 units and down 2 units. So that's going to go right 3 units and down 2 units. So yeah, you can imagine taking this, sliding it over and down. So instead of the vertex being at 0, 0, the vertex should be at 3, comma, minus 2. So 3 minus 2. So there's our vertex. And I think I'm going to cheat a little bit here and use a ruler. It's supposed to be a sketch, right? But, you know. It should look something like this. That should be 5. That should make sense why this x-intercept or root is 5, right? Because if x is 5, then I get a y value of 0, right? And it should make sense why 1 is a root or an x-intercept here, because if x is 1, I'm going to have 2 minus 2, which is 0. But the important part is that this is the graph of this pushed to the right 3 units and down 2 units. All right, so as mentioned before, we could apply our translation techniques to other functions in our library. So let's try to sketch the following. So let's try to sketch y equals the square root of x minus 5. Of course, we want to keep in mind our parent function. So the parent function is y equals the square root of x. Remember what that looks like. Looks like this. And so as a translation, this will take this graph and push it 5 units to the right. Makes sense. Play that game. Follow the vertex. Here, what choice of x creates a y value of 0? Well, if x is 0, y is 0. Here, which x creates a y value of 0? If x is 5, so that was slid over to the right 5 units. An x value of 5 creates a y value of 0. Follow the vertex. Okay, let's say that's 5. And as a light sketch, I think that's perfectly fine. Now, as a quick extension, what if I had the following? So say I wanted to sketch y equals the square root of x plus 5. Well, if I wanted to sketch this, let's play follow the vertex. What choice of x here creates a y value of 0? Well, if x is 0, y is 0. But in this case, which choice of x creates a y value of 0? Minus 5. So follow the vertex. Should look like this. So powerful, right? You can now look at this and have a mental image of the graph. All right, so let's look at one more example from our library, and then we'll move on to more translation rules. By the way, all of these horizontal and vertical translations that we looked at, they're referred to as rigid because they maintain the shape of the original graph. The translated versions are congruent geometrically to the original graphs. So let's sketch g of x equals 1 over x minus 4 plus 1. So let's recall the parent function. So the parent function is f of x equals 1 over x. That's what we refer to as a hyperbola. And we see graph in quadrants 1 and 3. There are some important features that we want to keep track of. Notice here that the graph never touches the y-axis. There's like this invisible dotted line. We'll define that more precisely later in the course. And notice that there's this sort of invisible line here where the graph never touches or crosses. Let's keep track of that. Let's see where these are translated here. Now here, from this part, will I be moving the graph left or right? Well, it looks like we're going to move the graph right 4 units. Now here, looks like I'm going to be pushing the graph up 1 unit. Okay, so let's keep track of these important guidelines here. So this will get shifted up 1 unit, this guideline right here. So that's really y equals 1 is that guideline. And here, this guideline will get shifted 4 units to the right. So let's say that's x equals 4. So we know we're going to have this shape here. And that's exactly this portion. And then we're going to have exactly this shape here. And of course, if you needed to, you could easily calculate the y and the x intercepts here. But for a sketch, I think this is just fine. Okay, so let's investigate further. So let's say we've got g of x equals minus x squared. So again, let's go ahead and make a table of values. Here's x, g of x equals negative x squared. So remember in math what we mean by this negative sign? It really means x squared first times negative 1. That's what that really means. A negative sign is really multiplication by minus 1. All right, so let's start by plugging in minus 2. And so again, remember how to think about this. By order of operations, we compute this first, right? So this is negative 2 squared. So that'll be 4 times minus 1. So that's minus 4. So of course, remember you're following order of operations. Plug in minus 1. So minus 1 squared is 1 times minus 1. So 0 squared is 0 times minus 1 is still 0. 1 squared is 1 times minus 1, etc. Okay, so we've got some points here. Again, we can give a very, very rough sketch, which is just fine. And we don't need any positive y's, do we? Okay, so minus 1, minus 2, minus 3, minus 4. I like to give at least one more for good measure. Why not? Okay, so minus 2 comma minus 4. Minus 2, minus 4, right here. Minus 1, minus 1. 0, 0. 1 minus 1. And then 2 minus 4. Okay, so it looks like we have something like this. And so interesting. So it looks like when we negate all the y values, we reflect through the x-axis. Let's see if that makes sense. If I negate the y value, that's a reflection through x. So let's take the point xy, make sense of that. So I just claimed if I negate the y value, that's a reflection through x. And that's true. So if it looks like if we negate the y value, that's a reflection through the x-axis. So that'll tell us how to flip graphs upside down. Now let's do another investigation. What if we negate the x value? Let's do maybe a little prediction. So this was us negating the y value, and this yields a reflection through the x-axis. Now, as a little, like I said, a little pre-investigation, let's see what happens if we negate x. So let's say here's the point xy. If I negate x, that means I'm symmetrically on the other side. That's negative xy. And you can see that, yeah, if I negate x, that's a reflection through the y-axis. So negating the x value yields a reflection through the y-axis. Okay, so negate y. So take your old outputs and negate them. You got a reflection through x. Through this observation, we're saying if you negate x, you get a reflection through the y-axis. And now let's do an investigation with a function that sort of maybe hints that that's a reasonable thing to think. So investigation, so g of x equals the square root of negative x. Now, what you don't want to do is you don't want to look at this and say, oh, I can't have the square root of a negative. I haven't told you which x's we're using. So you don't want to assume that this quantity is negative until you sort of reason through which x's are appropriate to plug in here. So we definitely want to think about this in the right way. So let's get the parent function. So there's the parent function. And let's see if we can reason through this without a table. Okay, so if I'm looking for valid inputs for x, I don't want to plug in any positive number here. If I plug in a positive number, I'll be taking the square root of a negative, and that's not defined for real numbers, and we're looking at functions of a real variable. So I don't want to plug in any positive x because that would be problematic when dealing with real numbers. So what's the largest choice of x so that this is defined? Well, the largest x that I could plug in here so that this is defined would be 0. If x is 0, this is defined because the square root of 0 is 0. Now, which types of x's are appropriate to keep this defined? I want negative x's so that the double negatives create a positive input for my square root. And if that's the case, then I should get exactly this. So that's interesting. Negate your x, and it's a reflection through the y-axis. So g of x equals negative f of x is a reflection of f of x through the x-axis. And then g of x equals f of negative x is a reflection of f of x through the y-axis. So now, of course, we can combine things. We can shift things left, right, up, down, but also reflect them through the x-axis, through the y-axis. So let's say we want to sketch g of x equals minus x plus 1 quantity cubed. And of course, we want to think about the parent function. And so that would be f of x equals x cubed, which we know has this shape to it. And we want to think about the two transformations that are happening. So this portion is going to move the graph to the left 1 unit. So imagine sliding this over to the left 1 unit. Right? And then this is going to reflect through the x-axis, right? If you negate the y, this would be the output, the y. If I negate the y, you will reflect through x. So this portion comes up and this portion goes down. Okay, so the first thing we can do is follow the vertex, not the vertex, the inflection point, because it's x cubed, right? Follow the inflection point. So there's the inflection point. Left 1 unit. And then reflection through the x-axis. So we don't want this. We want this. That's the idea. Again, it's not perfect, but it's enough for a sketch. It's perfectly fine. So you sort of get the idea to the reader. Maybe that's a bit better. Okay, so let's note something. So let's note. So vertical translations, horizontal translations, and reflections are examples of rigid transformations. And what we mean by rigid transformation is a transformation that doesn't change the shape. It would still be congruent after you performed one of these to the original graph. So these rigid transformations do not change the basic shape. Doesn't matter if it's reflected, it's still sort of the same basic shape. And this sort of maintains congruence. Geometric congruence. Well, now what we want to do is we want to look at non-rigid transformations. These are your dilations and that stretch and shrink. Okay, so these are the dilations. So for example, let's say I wanted to investigate. Let's see if we can reason through this without a table of values. So let's say we wanted to investigate g of x equals 2x squared. So you can imagine this is sort of like a dilation by a factor of 2. Okay, so reasoning through this. So let's say that I'm actually going to draw the parent function as like a dotted graph. So let's say that the parent function, of course, is y equals x squared. So this is not the graph of this. This would be the graph of y equals x squared. Okay, so let's see what's happening. So for every x, do you notice that the y value here is getting doubled? That means that the graph is going to increase in the direction of infinity faster. So that for this graph right here, which will be sort of the solid, and this one was dotted, I'm going to have something that looks like this. So it's compressed towards the y-axis. And it makes sense again because the y values are being doubled, so you're going up faster in the direction of positive infinity. And what you'll find is the larger that this coefficient is, the more of a compression towards the y-axis you get. So if I had, 10x squared, I could imagine that being very, very compressed towards the y-axis. And so you notice this compression inwards if this constant c, so in this case, c equals 2, so I get this compression. So if c is, I want to say larger than 1, so if this constant is larger than 1, we get this sort of compression. We get this vertical compression. Towards the y-axis. And that's for like, g of x equals c times f of x. So the next thing that might be interesting to ask is, well, what happens if c is, I don't want to talk about negative quite yet because we said negative values of c were reflections, right? But what happens if c is between 0 and 1, right? So let's say this is the second case of g of x equals c times f of x. And so let's say in this case, we want to investigate g of x equals 1/2 x squared. So this is if c is specifically between 0 and 1. And so let's play the same game. Let's draw the parent function. Okay, so there's the parent function y equals x squared, y equals x squared. And then in this case, notice that the coefficient in some sense is slowing down the y values. For each x, this y value will be half of what this would have been. So for example, if I picked x to be 6 here, the y value would be 36, right? So I have 636 way up here, right? In this case, if I picked x to be 6, the y value would be half of 36. So it's slowing it down. So instead of compressing towards infinity faster, it's going to slow it down. It's going to open up. It's going to take longer to go in that direction. And so I get this sort of wider parabola, wider graph. It's sort of opened more towards the x-axis. Right, the y values they're chilling out of it. They're not in a rush to go towards infinity in some sense. And so what happens is, as c gets closer and closer to 0, this gets wider and wider and wider. It gets closer and closer and closer to the x-axis. And that should make sense, because what happens if c is 0? If c is 0, you get exactly the x-axis. So the closer c is to 0, sort of the more this sort of opens up, it gets wider and wider and wider. If I had a 10th of x squared, I have this really sort of slow, wide parabola. So if c is between 0 and 1, I do get this vertical expansion, but towards the x-axis. Right, a fractional coefficient is slowing down your y values. So it's not going in the direction of infinity so fast. It's taking a bit longer in some sense. Okay, so let's look at this idea of compression and mix it in with translations that are vertical, horizontal, as well as reflections. Let's throw everything in right now. So what we want to do is now look at let's say y equals the absolute value of x as a parent function. And maybe let's compare that to y equals minus 3 times the absolute value of x minus 4 plus 7. And let's compare all of these to y equals minus 1/3 absolute value of x minus 4 plus 7. So before we even think about looking at the graphs, let's make some predictions. Can we look at the algebra here and get a mental image of the graph? Well, I'm thinking about my parent function. So right now I'm looking at b. I'm thinking about b. In fact, let's separate it and really just pick apart all the pieces. All right, let's think about this because there's 1, 2, 3, 4 ideas that we need to tackle here. So this part, this is going to be a translation to the right by 4 units. And when I say right, this is in relation to the parent function, the absolute value of x. Absolute value of x will also go up 7 units. What does this 3 tell me? So if this is absolute value of x, this 3 is going to give me some compression in this way. It's going to be like a tighter v in some sense. Okay, so if here's absolute value of x, right? It's going to move over 4, up 7. It's going to be tighter, right? It's going to have a vertical compression towards y. But then what does that minus tell us? It's a reflection. Okay, so over 4, up 7, a tighter compression towards y, and upside down in a sense. Stretched by a factor of 3, and then reflection. I don't want to say upside down, I want to be a bit more precise, but reflection through the x-axis. So knowing all this says I can look at an equation like this and get an instant mental image. So let's see how we did. So here's our parent function right here. And then let's see here. So this was moved to the right 4 units, up 7. If you look at the scale, that's fine, right? Because that would be 7. And again, if you look at our scale, we're fine. Looks like 2, 4, 6, 8, 10. So there's 4. Notice that it is compressed a lot more compared to this, so that makes a lot more sense, or makes a lot of sense. And then also we have a reflection through the x-axis. So we've got this upside down v in formal terms. So yeah, that makes a lot of sense. Over, up, squished, upside down. Okay, so with that said, what should the last graph look like? What should part C look like? So there's really only one variation here, right? The variation is the 1/3. So we're still expecting to the right 4 units. We're still expecting up 7 units. We're still expecting a reflection through the x-axis. But instead of having that vertical compression, which makes it sort of a tighter V, it should be spread out more, but upside down. So over 4, up 7, reflection through x, and have a very spread out compression. Let's see if that makes sense. So here's our parent function. There's y equals absolute x. And here's the function that we wanted to investigate. And it has all the properties we said it would. It's been pushed over 4, up 7, reflection through the x-axis. So it's got this shape, this upside down shape that comes from a reflection. And then it's opening wider because the y values are increasing at a much slower rate. Okay, so now let's talk about sort of a horizontal shrink and stretch. So that was a vertical shrink and stretch. Let's talk about a horizontal shrink and stretch. And so in this case, we're looking at g of x equals f of cx. So before, actually, maybe I should say this, right? So for before with vertical shrink and stretch, that's what we just investigated before this. We were looking at this, g of x equals c times f of x. And we were able to look at a couple different cases, right? We were interested if c was greater than 1, and we said that the larger c was, the more sort of compressed towards y the graph got. And then we said, okay, what happens if c is between 0 and 1? And we said the closer that c was to 0, the more opened up our graph got. So that's what we just investigated. So now this case. Okay, so let's actually do this through an example. And let's be on the lookout for the following. So I'm going to have horizontal shrink when c is greater than 1 and stretch when c is between 0 and 1. So we're going to investigate this with this as our parent function. So we're actually going to use a translated version. And so imagine that we graph f of x equals 2 minus x cubed. So everything that we look at will be in relation to this, right? So if we were to graph this, how does this compare to x cubed? Well, it's going to be a reflection through the x-axis that's pushed up 2 units. So it's not going to have this shape, right? It's going to have this shape, but pushed up 2 units. So the inflection point should go through here, right? It should have this kind of shape to it. Okay, so yeah, we're going to look at an example of this and this, but in relation to this graph. Okay, so sort of what we're comparing to is this, and we want to look at y equals 2 minus the quantity 1/2 x cubed. So that's specifically the case where c is between 0 and 1. And then we also want to look at y equals 2 minus quantity 2x cubed. And this is the case where c is greater than 1. Okay, so if we take a look here, so all 3 of the graphs are drawn and they're denoted in different ways, right? So 2 minus x cubed, that's the solid graph right here. So 2 minus x cubed is the solid graph right here. So 2 minus 1/2 x cubed is the dotted graph. So this dotted graph right here, this is the case where c is between 0 and 1. Notice that it's stretched, right? It's more stretched out like this. And that's, again, maybe that's not a huge surprise because the y values are still being slowed down. I mean, imagine cubing both of these. So you'd have your this would be sort of slowed down a bit. And then the dotted, oh, no, the dashed line here goes with this. So this is this graph, and this is the case where exactly C is greater than 1. And that's a horizontal shrink. And it makes sense that it's sort of shrunken and more compressed because the Y values are sort of increasing more rapidly than this, right? So that's going to be much tighter towards the Y-axis if the Y values are increasing very quickly or decreasing very rapidly compared to this. So that seems to make a lot of sense here. So again, here when C is between 0 and 1, so you notice that you've got this stretch because it's sort of slowed down a bit, right? The Y values are sort of slowed down, and you're seeing that right here. In this case right here, where C is greater than 1, you're noticing that it's more compressed. The Y values are spread. I'm sorry, the Y values are increasing more rapidly. So you're going in the directions of positive infinity quicker. So if I'm tighter towards the Y-axis, that's what's happening compared to this. So slow. So stretch here, C between 0 and 1. And then you've got this shrink or closer to the Y-axis when C is greater than 1 here. You're going to infinity faster. Okay, so put a lot of time into this practice. It is a very useful, handy skill. It extends well beyond calculus, right? You'll use this in science classes, economics classes, business classes. Understanding the behavior of graphs is incredibly valuable.